There's no point having a theory about how organisms are songs and how they orchestrate evolution if you can't explain where the songs come from. So that's what part 3 is for. I'm going to be talking about second-order optimization processes, cognition as dynamics in implicate and explicit order simultaneously. Okay, so let me briefly do an overview of part 3. Natural selection is not the only possible mechanism by which a system can get better by itself without design. Learning is a transformational process of adaptation. It doesn't depend on variation and selection. Learning occurs spontaneously in suitable substrates. That's the mechanism of natural induction, which I've shown how to operate in a network of viscoelastic connections, a dynamical system described by a network of connections which are viscoelastic and subject to perturbations, exhibits adaptation spontaneously. I'm just recognizing what a mouthful that is. And it shows an improved optimization ability without any selection being involved. If natural induction can show adaptation spontaneously, what else can? The underlying principle is direct induction from the environment, which folds the internal architecture of the dynamical parameters. And my conjecture is that it doesn't really need a physical network of connections to do that. Connections can be resonance between oscillators instead. And that happens spontaneously in songs, the dynamical systems with harmonically coupled layers. And in that substrate, it has the deeply recursive reversible learning process that we were looking for. And it still connects with all of those other lovely properties in the list of desiderata. So first, natural induction. Natural induction is a spontaneous problem-solving process, a different source of adaptive organization, an inductive associative learning process. This is work developed with myself, Chris Buckley, and Mike Levin, and Tim Lewins. What is inductive associative learning? Well, that's just learning what goes together. Donald Hebb described a process of learning in neural networks where neurons that fire together wire together, which sounds like it's specific to the neural substrate, that it's something clever that neurons do, probably because natural selection programmed them to do it. But it's really a very simple dynamical principle of positive feedback on correlations. The more two things co-occurred in the past, the more they become likely to co-occur in the future. Two neurons that are both stimulated by this at the same time, or one shortly after the other, create a causal connection between them that means that now if one of them is stimulated, it stimulates the other one. It makes an internal connection that makes a causal process out of an external stimulus that was a correlation. Now, in the context of artificial neural networks, that can do all sorts of cool things, including learning to solve constraint optimization problems better with experience. Now, brains and machine learning systems are selected or designed for the purpose of doing induction, but natural induction occurs spontaneously in dynamical systems with suitable properties without being selected or designed for that purpose. The conditions for it to occur are a dynamical system described by a network of viscoelastic connections and that is subject to occasional disturbances. So what kind of dynamical system isn't described by a network of connections? Well, they all are, but the special thing is that the connections are viscoelastic. That means that the connections give way slightly under stress. That if you have a perfectly elastic spring, for example, connecting two masses, you can elongate the spring and then let it go, extend the spring and let it go, and it goes back to exactly the same length. Or you compress it and let it go, it goes back to exactly the same length. That's a perfectly elastic spring. But that's a fantasy. No spring is perfectly elastic. In fact, if you stretch a spring too far or too long, when you let it go, it doesn't quite go back all the way. That's a slightly plastic or a slightly viscous spring. Together, it's still a bit elastic, so it's a viscoelastic connection that gives way under stress. The gist of the natural induction algorithm, process, phenomenon has two parts. That physical systems optimize spontaneously, in a weak sense. And physical systems learn spontaneously in a weak sense. But when optimization weakly informs the learning and the learning weakly informs the optimization, that coupled process creates a physical system that learns to optimize better with experience. That's the gist of the whole thing. So physical systems optimize spontaneously just in the sense of, well, if I have a dynamical system described by a bunch of parameters, then that describes the dynamics of the system. It moves to a local minimum in the energy function. If those parameters of the dynamical system constitute the constraints of a problem, as Hotfield and Tank showed in the 80s, then running the network, just running the dynamical system with those parameters, finds you locally optimal solutions to the problem, but only locally optimal solutions. It's not a very good optimizer. This is first order optimization, exactly like natural selection, by the way, that the shape of the landscape pushes the state dynamics, pushes the state of the system into a local minimum in the energy function or potential function. Exactly the same as saying the selection coefficients push the allele frequencies to a local peak in the fitness landscape. Physical systems can also learn spontaneously. Menachem-Stern showed lots of different substrates, which have been shown for both supervised and unsupervised learning. One of my favorite ones is learning in origami. So you fold a piece of paper, and the first time you fold it, it resists a little bit, and it only folds one way more easily than another. But if you fold it in a particular way more often, then it becomes easier to fold that way. And then as you unfold it, it pushes back in a way which is specific to the way in which it's been folded in the past. The creases give way a little under stress. So that in those different substrates, the details are various, but the principle is still very simple. You have a dynamical system described by a network of interactions, and you push on it. In other words, you provide a data item or an experience, an interaction with the world, and the interactions internal to the system give way. The internal structure of the system gives way slightly to accommodate the frustrations in the system given the current state of the system. Now, the physical optimization and the physical learning are really just two different sides of the same coin. Physical optimization, you have the same system that you're relaxing by relaxing the state variables in the case of physical optimization, or relaxing the structural variables in the case of physical learning. It's the change in the parameters given the state, or the change in the state given the parameters. Neither of those is very interesting on its own. It's not very interesting to say, look, I crumpled this piece of paper, or look, this ball rolled downhill. But when we put these two things together, we get adaptation by natural induction. Optimization weakly informs the learning. In other words, the position of the ball on the landscape wasn't arbitrary. It was a local minimum in the landscape. It's not a very good solution to your problem, but it's better than a random one. So the paper crumples in a way that's sensitive to the position of the state. Then you pick the ball up and you roll it down the landscape again, and now it rolls slightly differently because the landscape is deformed slightly. It finds a local minimum in the new landscape, and that becomes the next data point for deforming the landscape, and so on in an iterative fashion. And the feedback between those two processes creates a dynamical system that finds solutions that are better than the locally optimal solutions found by the original system. Here's a numerical simulation. We have a system of masses connected by springs, and these springs, the dark blue ones, these are the ideal springs. They're the problem. They can't be changed. You randomize the position of the masses and you let it go, and the springs push the masses around until they find an equilibrium. That's not adaptation. That's just finding a nearest local optimum. It is first order optimization. Now let's separate the problem from the learner. Oh, sorry. First, we will do that many times by randomizing the position of the masses again and letting them equilibrate, randomizing the position of the masses again and letting them equilibrate. Each time we do that, it finds a local minimum, but because the spring constraints are complicated, it finds a different local minimum each time you run it. The springs aren't changing. So this is still boring. We're just exploring the dynamics of the system. Where are the local minima? And how good are the local minima at resolving the frustrations in the springs? The vertical axis is the energy of this in the springs of the original springs, right? If you find a local minimum, it's going to be lower energy than a random configuration. But since there are many local equilibria, they will have different energies. And that's what's being plotted here. Now we add to this another system of springs. This is the learner. The learner is initially an even blanket of relatively weak springs that don't affect the dynamics of the system because on average they cancel each other out. But these springs are viscoelastic. And over time, they deform according to the ways that they get pushed by the masses as they move over multiple disturbances. And that means that some of the deformable springs give way and other springs don't. And then as they accumulate structure, that some are consistently changing and some are consistently not. Some are consistently changing one way and some are consistently changing the other way, slightly increasing or decreasing their natural lengths. That does change the dynamics of the masses, even though they're still connected to the problem springs. And over time, what we observe is that the system finds configurations which are exceptionally good in their ability to find configurations that resolve constraints in the problem, the blue springs. That's adaptation. So the system with the learning springs and the blue springs together, the problem springs, the learning springs model the dynamics of the masses controlled by the blue springs, but they model it in such a way that changes it, that changes the dynamics of the masses. They push back. And in the pushing back, they change the dynamics of the system. How do they do it? They harmonize it. They make it easier for it to find configurations that have less stress. So the ideal springs which didn't learn have energies which are all high. The system with the learning springs converges on a configuration eventually that it always goes to the same place. And the place that it goes to is lower than the energy of any of the configurations that were found before learning. So it's not just taking one of the good ones and reinforcing it like a memory. It's proper adaptation that it is reaching beyond the local equilibria which have been sampled in the system before. This is a stronger optimizer. It's a second order optimizer that appears to go downhill better than going to the nearest local minimum. If we were going uphill, we would say, hey, look at that. It ignored the local gradients and went to the global optimum instead of the local optimum. It isn't just rolling downhill, it's second order rolling downhill. The springs, the ball is rolling downhill, but the springs are also rolling downhill. The landscape is just giving way. It's just relaxing. That's a kind of rolling downhill. But those two kinds of rolling downhill at the same time, second order rolling downhill, gets better with experience. The more you sing it, the more harmonious it becomes. It changes the dynamics of the system. So natural induction isn't just a ball moving in the way that it's pushed. It's moving in the direction that it wants to go because it's being pushed by its internal push as well as the external push. The external push is the problem springs. The internal push is the deformed springs. That makes the behavior look agential. Agential means you didn't just go to the way you were pushed, you went somewhere else that was better than that. This is as much a theory about how the landscape changes as a theory of how the ball moves. And it's about the feedbacks between how the changes in the state variables change the relationships between the state variables and feeds back on each other. It's exactly what we didn't have in the first order optimizer way of understanding natural selection. So this gives us a global adaptation ability. And in the context of an artificial neural network, we sort of understand that that's not so surprising. We have a system of neurons that fire together, wire together, which is just positive feedback on correlations. The more two things co-occurred in the past, the more they become likely to co-occur in the future. And that produces something clever with a global adaptation ability. But this shows that if you have a dynamical system described by a network of connections that give way slightly under stress, then that makes the current state configuration more likely to occur again in the future, positive feedback on correlations, which makes the springs learn in exactly the same way that associative learning changes the dynamics of a neural network and gives exactly the same global adaptation ability that you get in a learning neural network. So as the structure of the relationships between entities change, the system becomes more than the sum of the parts. It becomes organized such that it exhibits systemic intelligence in the sense of showing a problem-solving competence that improves with experience. We can also understand this in a Fristonian way, that the deformable springs are mirroring the problem springs through an interface, which is the masses that share their connection. But it isn't just mirroring it in the sense of making a perfect model, because together they have a dynamics which is different, that the original system plus the model has a dynamics which is different from the original model. And the dynamics of the coupled system is collectively minimizing surprise. So it isn't just a passive model, it changes the dynamics and more specifically improves the dynamics in the sense of finding configurations that better resolves constraints among its components. But resolving constraints among your components is exactly what happens when you push on the pylon or you do deep learning in an artificial neural network, right? Okay. Now, this is just what dynamical systems do. You don't need to engineer special springs to do this or arrange them in any particular way. If you just have a dynamical system described by a system of masses connected by interactions which give way under stress, they don't have to be springs, of course, anything that gives way under stress will have the effect of doing this kind of associative induction. We can understand what's happening here as just second-order relaxation. The state variables are relaxing into a configuration, and correlated observations over time of those state variables changes the connections. How does it change the connections? Well, the connections just relax in the way that's easiest for them, the natural length that's easiest for them. They're pushed into a different natural length by the correlated state changes in the states. And now that they have a different length, they push back. The connections change the state correlations, the dynamics of how the lower level variables work. Second order relaxation is smarter than first order relaxation. The connections form a generalized associative memory over past attempts, which we can understand as a type of associative learning. Now, natural induction and natural selection are not the same algorithm. Natural selection works by differential survival and reproduction of entities. It's a variational process. Natural induction works by the differential easing of frustrated relationships between things. It's a transformational process. If you like, natural selection is a substance tautology. It's about things and their frequencies, whereas natural induction is a processual or relational ontology. It's about things changing organization over time. Because they're different mechanisms, it applies to different things. Natural selection can't apply to an ecosystem except in special cases where it's encapsulated in a way that makes it into a new evolutionary unit. And it can't apply to the biosphere as a whole because it isn't an evolutionary unit. But because natural induction is a different mechanism, it can apply to different things. If it was the case that the feedbacks between different components of the biosphere gave way under stress and the whole biosphere was subject to repeated shocks or perturbations, it would do the same kind of natural inductive learning. They're also different because it has different adaptive capabilities. One is first order optimization, the other is second order optimization. And they're also different because the product is involved in the process. That's what it means to be a learning process and not just a variation and selection process. Now, it's interesting that one is variational and the other is transformational. To emphasize that the natural induction model is not natural selection, there's no reproduction of masses, there's no reproduction of springs, there's no reproduction of networks, there's no random variation selection, there's no macro scale process telling it how it should change or how it shouldn't. It's just internal giving way. Now, it's interesting that they're different mechanisms, that one is variational and the other is transformational, and that it does it without using two levels of selection. There's no population of networks. But the more important difference is that natural induction is second order and natural selection isn't. Let's expand on that. I mentioned that second order relaxation is smarter than first order relaxation. What's really going on here is that we have a sort of a first order structure, the original space of all of the problem variables. And then there's a second order structure, which is about the springs. What are the configurations of the springs? And when you're doing relaxation in both those spaces at the same time, you get something smarter than just doing it in the original space. You can't just do it in the other space either, because it wouldn't be connected to anything. So there's a first order structure that changes the parameters of the higher order structure, which are the parameters of the first order structure. There's a feedback between those two different levels of organization. What if we add a third or more? If we do this recursively, not recursively, if we do this over multiple levels, we can implement that algorithm in a deep auto-associative network in machine learning techniques, where you take a problem space, you run a hill climber on it, you find local optimal solutions using the hill climber, you use compression to make a model of those solutions, and then you run a hill climber in that space. Hill climbing movements in that space are non-local movements in the lower space, and they find better optima than the first one. That's what natural induction shows. But then we go another level and we say, now we're going to look for correlations in those solutions, and so on and so on and so on. So as we go up the autoencoder, we're compressing the space. Then we do movements in the compressed space, and then we decompress it back to a solution and see where we got to. And then we can do movements that in the original space look like they were jumping over local energy barriers, or going across a fitness valley and up the other side, or going over an energy barrier and down the other side if we're minimizing. So an ordinary uninformed relaxation in the compressed space produces an informed or agential relaxation in the problem space. And that's actually quite a clever optimization method. It solves problems that single-level optimization processes like evolution or other quite sophisticated model building optimization algorithms can't solve. The significance of that with respect to biological interpretations is discussed in our paper, Design for an Individual, where we describe the possibility that evolution is a multi-scale associative learning machine. Now, let's think about this from a cognitive point of view, where we think about program and data instead of order of structures, that each level's program is data to the level above, and each level's data is program to the level below, coupled upwards and downwards. We're moving the organization from one level of structure to another in a way that's reversible, that little changes in this one changes the structure above, and the structure above can push back down to make little changes in those. That much folding we can do in a way that's reversible. But if this is reversible, and that is reversible, and that is reversible, we end up with a deep system that is reversible. It's also the case that each little step, each level, is a folding of the space below that's underdetermined, so that it's a compression of the space, which also gives you a generative recall, that you get one concept, many instances. The change in the structure that is high order structure needs to be slow compared to the low level structure, which is fast. That each level is a structural constraint when viewed from below. It's a constraint because it hasn't changed, but it is changing really. It's just changing more slowly. So as you go up to the next level, that looks like a variable to the level above, which is changing even more slowly. So it looks like a constraint, like it's not moving, like it's a parameter, not a variable. It is a variable. Really, it's just changing more slowly, and so on. And the effect of coupling together those dynamics across those different folded scales is you end up with something where movements at the top scale, which look uninformed and obvious and local, correspond exactly to informed agential non-local movements in the high dimensional space. This is what's suggested by David Bohm in his interpretation of quantum physics, where there's an implicate order where everything is connected. And there's an explicate order where it seems to have many different instances of things which don't seem like they're connected. But they are connected because they're really the same thing in a different space. In computational terms, we would think of the implicate order as being a concept, something that's symbolic, something that's a single, unified, idealized idea, an induced general rule, induced from many specific, messy instances. Whereas the explicate order is grounded. It's that concept attached to particulars of the physical substrate, many specific instances which can be deduced from the general rule. And abstraction is the process which goes upwards, and generation is the process which goes downwards. Induction is the folding of the space, and deduction is the unfolding of the space. Another word about substance versus process. Natural induction is transformational, not selection-based. It's not about separating what to discard from what to retain, a winnowing process. It's not about what persists exists, where there isn't actually anything new, and you only get first-order adaptation, like you get in a substance ontology. It's not differential survival and reduction of things, but the changing relationships between things, transforming, which creates something new, something smart, something more informed. It's about what relates creates rather than what persists exists. It's a processual and relational ontology. So I'm moving now from an idea of masses connected by springs and solving optimization problems to a folding of space that constitutes an algorithm or substrate for life and mind.